Good afternoon, everybody. Sorry about today. The annotator got really mad at me for coloring the other day. Doesn't want to work with Zoom anymore. So got to record this offline. Today we are continuing to talk about pipes, and today we're talking about major and minor losses in pipes. And it turns out that the major losses in pipes usually are those due to friction. The minor losses are due to things like 90-degree turns, fittings, valves, etc. So let's get started. I'll go over to the annotator and we'll get going. All right, here we go. Okay, so talking today about major and minor losses, and then we'll look at a couple of examples, single pipes, multi-pipe systems. I've got non-circular conduits here in the sort of menu for today, but turns out that I'll probably just barely have time to squeeze everything else in, so I'm going to let you read about that in the book if you're interested, and I promise not to give any problems with non-circular conduits. Okay, so major and minor losses. So the head loss term from the energy equation that we're all familiar with can be divided into major and minor losses. And yay, by the way, the annotator's working. And furthermore, the major losses are written in terms of a quantity called the friction factor. Okay, this is a really important equation. So we'll box this. We're going to use this all the time in pipe flows. It's equation 834 in the textbook. So for laminar pipe flows, this friction factor is really straightforward. It's always just 64 over the Reynolds number, right? This is equation 819. And if you remember, the Reynolds number is basically the normalized velocity in a fluid flow. So you take the velocity and you non-dimensionalize it using the pipe diameter, the viscosity, and the density of the fluid, and you get this thing called the Reynolds number. For pipe flows, if your Reynolds number is below about 2100, you know you have laminar flow for a smooth pipe. If in a smooth pipe your Reynolds number is greater than about 4,000, you know it's turbulent flow. In between those two numbers, you're in the transitional flow regime. All right, well, what about turbulent pipe flow? Well, here, the friction factor is a function of both the Reynolds number and this quantity called the relative roughness, epsilon over d, where E is the roughness of the pipe and something that you look up in tables for a given material. All right. So if we have only major losses in a fully developed pipe flow, we can rewrite the energy equation as follows in terms of a pressure difference between the two ends of a pipe, a length of pipe. It's equal to gamma times the difference in heights plus gamma times the head loss. But if we write the head loss out, this becomes Z2 minus Z1 plus F L over D V squared over 2G, right? So that's that major loss term. And how do we find this friction factor epsilon that goes into finding F? Well, we consult table 8.1, right? So it tells you for these different types of materials what the roughness itself is in both feet and millimeters. And the trend is, if you look here at the friction factor for a turbulent flow versus the relative roughness, so the roughness divided by the diameter of the pipe, it really, really increases with relative roughness, right? So we've got this exponential increase in this friction factor with an increase in epsilon over d. It's not linear, it increases really drastically with relative roughness. Okay, now we come to the Moody Chart, and I'll just take a moment to say that the Moody Chart was developed in the same dusty, dungeony basement laboratory where I did my PhD in the engineering quad at Princeton. So I breathe the same air molecules as Moody. Okay, so you've got a turbulent pipe flow. You've looked up the roughness in table 8.1. You've divided it by the diameter of the pipe. So now you know what your relative roughness is. So now the first thing you do is you go to these curves and you try to find the right curve for your relative roughness. Let's back up a moment. So here, this straight linear curve with the negative slope, this is the curve for a laminar flow, right? So friction factor for a laminar flow is always 64 over the Reynolds number. We've got on the horizontal axis the Reynolds number. On the left vertical axis, we've got the friction factor. And then on the right vertical axis, we've got the relative roughness, but this is really just telling you which of these curves to choose, right? So here you've got laminar flow until a Reynolds number of about 2,000. And then this line becomes dashed because between 2,000 and 4,000, we're in the transitional flow regime. And then at 4,000, we've got all these turbulent flow curves, and you choose one depending on your relative roughness. So let's say we have a relative roughness of 0.03. We come over here, we know this is our curve, right? So now we choose the point along this curve that's equal to our Reynolds number. So let's say our Reynolds number is 10 to the 5th. So we trace it up to our relative roughness curve, and here we go. They intersect approximately here. And now we trace this back to the left y-axis to find our friction factor value. It's, about maybe 0.058, something like that for that particular flow. There's not a lot of accuracy when you're doing these pipe flow calculations, right? You've got to sort of eyeball friction factors off a chart or use an equation like we'll see on the next slide that's not terribly accurate. So a rule of thumb for turbulent pipe flow is about 10% accuracy is fine for pipe flow problems. All right. Let's say you don't like that chart, the Moody chart, and you want to use an equation. There are two that I'll give you. So the first one's called the Colebrook formula. And it's 1 over the square root of the friction factor is equal to minus 2.0 log base 10 of the relative roughness over 3.7 plus 2.51 over the Reynolds number times the square root of the friction factor again. So then this is equation 835A. So the fact that we've got this friction factor showing up again on the right-hand side kind of messes things up for us. It means we can't isolate the friction factor or the square root of the friction factor on one side of the equal sign and just solve for it, right? This is an implicit equation for F, and it needs to be solved iteratively, right? So that's no good. So I'll give you another formula. It's called the Haaland equation. And it's an approximation to the Colebrook formula, and it's slightly less accurate. So here we've got 1 over the square root of f again, equals now 1 minus 1.8 log base 10 E over D, or epsilon over D over 3.7, now raised to the 1.11 power plus 6.9 over the Reynolds number, right? So we've gotten rid of that square root of f on the right-hand side of the equation, so now it's an explicit equation for f, which is good, but you lose a little bit of accuracy. All right. So that's the subject of major losses, pretty straightforward, right? You've got a term, HL major, and it really is just losses due to friction at the pipe wall. The second type of losses are the minor losses due to pipe fittings, turns, valves, things like that, right? So if you look at this picture over here, you've got this T-junction, and it's got some internal structure like this. Well, of course, that really messes up our nice straight uniform flow, and you get these sort of chaotic looking streamlines, and there are losses associated with that, right? So the minor losses can be written in terms of a loss coefficient K sub L. All right, and this is the other really important equation that we're going to use all the time. It's 8.36. And K sub L is a function of both the geometry and the Reynolds number. All right. So let's look at some loss coefficients for different settings. If you have flow entering a pipe, you have a loss coefficient associated with that. So if you've got re-entrant where the pipe is, let's say that this is a large tank or container, right? You've got the pipe sticking into the container like this, you've got a loss coefficient of 0.9 associated with that. If you have up on the upper right a sharp edge, 90-degree turn, you've got a loss coefficient of 0.5 associated with that, right? Down on the bottom left, if you've got slight rounding, you've got a loss coefficient of 0.2, really well rounded, very low loss coefficient of 0.04, right? Because it's easy for the flow to sort of follow and turn that corner. If you look up here on top right, it's much harder for the flow to make that 90-degree turn, right? So there are a lot of losses associated with that. And this is figure 822. So now let's look at this case of a rounded entrance a little more closely. You can actually pick off your loss coefficient depending on your degree of rounding, right? So here you've got your entrance and you've got a radius of curvature associated with this entrance and a diameter. If you normalize, if you divide the radius of curvature by the diameter, then you can just pick off what your loss coefficient is, right? And so if your radius of curvature is basically 0 and you've got that sharp edge case again, right, you recover this factor of 0.5 for that 90-degree edge, right? And then as the corner softens, the loss coefficient drops off and drops off until it sort of bottoms out way down the chart. All right. For exits, if you've got a pipe that's exiting into a large tank or into the air, you know, this situation here with a nozzle, garden hose type of thing, loss coefficient is always 1, no matter what. Doesn't matter if it's a sharp corner or rounded corner, always 1. All right. What about if you have a sudden contraction, right? So you've got a pipe flow here, and then suddenly it is joined with another pipe which has a much smaller diameter, right? So we've got this discontinuity. Well, here, if you divide the two cross-sectional areas of the smaller pipe over the larger pipe, then you can pick off your loss coefficient again, right? And so here, if we imagine that A1 is much greater than A2, we've got a limiting case, right? Say A1 is so large, it really becomes that situation again where you've got a tank and you've got flow entering a pipe from a tank, right? So in this case, when A1 is much, much greater than A2, then basically A2 over A1 becomes 0, and you recover, again, that 0.5 value for an entrance with that 90-degree sharp edge. What about the opposite case, sudden expansion? A smaller pipe suddenly changing to a much larger pipe. Same thing, divide the cross-sectional areas, and you can pick KL off the vertical axis here. And here, again, we've got this limiting case. Here, we've got A2 much, much greater than A1, so that A1 over A2 is essentially 0. Well, it's like when you have a pipe just exiting into the free air or into a tank, right? You've got that exit coefficient, which is always 1, right? That's our limiting case here. Well, what if we have a conical diffuser, right? So you've got a nice circular pipe, and then it becomes a larger diameter, but not suddenly. It just increases in radius in an axisymmetric way. And the increase happens over such a length that it makes this angle theta, okay? Well, here, you determine what the angle theta is. Let's say it's 60 degrees, trace that number up and find your curve, trace this back to the y-axis, and then this quantity, KL over 1 minus A1 over A2 squared, is 1.2. Right? So you've got to do just a little bit of algebra remaining after that to find out what the actual value of KL is. All right, what about bends? So flow along a pipe and then it takes a 90-degree turn in any direction. Well, when that happens, we generally have a little recirculation in the pipe. It forms a little vortex at the bend. And it takes a little while for those downstream of the bend, for those vortices to go away and for the flow to become fully developed again. And there's a loss associated with that. Again, looking up the KL coefficient here depends on the radius of curvature here of the bend. So you take that radius of curvature, divide it by the pipe diameter, and now it also depends on the roughness. So just like the Moody chart, you've got to figure out what your roughness is. If it's a smooth pipe, it's just your relative roughness is 0. So you take R over D on whatever line you're on, and then where they intersect, you trace it back to the y-axis here and pick off your value of KL. You can mitigate the effects of these bends if you use guiding vanes, right? Those little sort of spacers that guide the flow around and don't let these large scale vortices that are sort of on the order of the diameter of the pipe, don't let them form, right? So here, if we have a 90-degree bend with no guiding vanes, we get this recirculation zone downstream of the bend. And actually, if you were to measure the fluid velocity profile just downstream, you'd see that you've got over part of the cross-sectional area, you've got a positive flow, and then you've got a little bit of reversed flow where that vortex is. And you've got pretty high loss associated, KL equals 1.1. If you use guiding vanes in the same flow, you really reduce your loss. You get down to a KL of about 0.2. All right, and then we've got table 8.2, and it basically lists, I've got it on 3 different slides here. It lists many different situations, so different kinds of elbows, depending on whether they're flanged, you know, if you just put them together by sort of fitting them in together, or if they're threaded, so you have to screw them together. Depending on the degree of the turn, 90 degrees, 45 degrees. We've got 180-degree returns. We've got T-junctions, like this image here. We've got unions, like this here. It's just one pipe flowing into another pipe. And then we've got valves, which aren't shown here, but basically, normally in a problem, you'll be told, okay, there's a globe valve, it's fully open or it's slightly closed, something like that. And it usually has a symbol, a round with an X through it is usually a symbol for a valve. So you will be, for pipe problems with minor losses, you will be referring to this table, table 8.2 a lot. And you know, you'll be able to print a copy of that for your exam, your final exam. I should say your midterm, your final midterm, exam 3. All right, so here we are. We've got some examples. Let's see how far we get today through these examples before our 50 minutes are up. So first example is a single pipe system. So we've got this pipe, it's taking lots of turns, 90-degree turns. It's got lots of elbows. It's got a valve here. So we were just talking about how valves are denoted usually by a circle with an X through it. And then the final minor losses due to flowing through this faucet. Faucets weren't on our table, but it gives the loss coefficient for the faucet here. It's 2, right? So water at 60 degrees Fahrenheit flows from the basement up to the 2nd floor of a house or an apartment building through a pipe that's 0.75 inches in diameter. It's a copper pipe, and then they tell us nicely that that's drawn tubing, which is nice because on table 8.1 we don't have copper pipes, but we do have drawn tubing. And the flow rate is given 12 gallons per minute. And the flow exits through a faucet of diameter of 1/2 inch. And we need to determine the pressure at 0.1 down here in the basement, right? So we've got 15 feet here, 10 feet here, 5 feet, 10 feet, and then 20 feet. So we're going to be accumulating major friction losses along all those lengths of pipe. And then we've got minor losses associated with each of these bends, all 4 bends, this valve, and the faucet. Okay. All right, so let's go ahead and find the velocity throughout most of this pipe system here, right? So the diameter is 0.75 inches through the entire system except at the exit. So we'll call that entire velocity in most of the system, we'll call it V1. All right, so our velocity through most of the system is 8.7 feet per second. Now, it's important that they told us that it's water at 60 degrees Fahrenheit. That's not quite standard temperature and pressure. So we're going to consult table B1 to find out the values of density and all the properties for water at 60 degrees Fahrenheit. So the density is 1.0 0.94 slugs per feet per cubic feet. The viscosity is 2.34 times 10 to the minus 3 pound seconds per feet squared. And yes, this comes from table B1. Okay, we can also calculate the Reynolds number for this flow and just see, are we dealing with a laminar flow or a turbulent flow? So Reynolds number now is rho v d over mu. So plugging in the values we have, I'm going to get a little lazy here and not write down the units, but they're all on the page so you know what the units are. So our Reynolds number is 45,000. That's about an order of magnitude higher than 4,000. So we are definitely in the turbulent flow regime. All right. Okay, so the governing equation is the energy equation. We're going to use the version with head loss since we're asked for pressure. So if you're asked in a problem for either head loss or pressure, you should use the form of the equation that's got the head loss included. So this is equation 8.21. And it's P1 over gamma plus alpha 1 V1 squared over 2G plus Z1 equals P2 over gamma plus alpha 2 V2 squared over 2G plus Z2 plus the head loss. Okay. Now here, Z1 equals 0. Z2 is equal to 20 feet. P2 is equal to 0, right? Because it exits into the atmosphere. It's a free jet. And we can write down the value for gamma. It's just rho g, and it's 62.4 pounds per cubic feet. Also, V2 is going to be Q over A2, which is going to be 19.6 feet per second. All right. Now for alpha 1 and alpha 2, if you remember, those are the coefficients that compensate for the fact that you don't have a uniform velocity profile, right? And as we know, in fully developed pipe flow, we have a parabolic velocity profile for laminar pipe flow, or a plug-like, kind of a squared version of a parabola, velocity profile for turbulent flow. Here, we're going to assume that that turbulent velocity profile, because it's pretty flat, that it's basically uniform, and we're going to set the coefficients therefore to 1. Okay, so this then simplifies to P1 is equal to gamma Z2 plus 1/2 rho V2 squared minus V1 squared plus gamma times the head loss. And of course, the head loss is divided into major and minor head loss. And then just plugging in our numbers here, we've got 62.4 times 20 feet plus 1.94 slugs per cubic feet over 2 times 19.6 squared minus 8.7 squared plus gamma times the head loss. So this turns out to be 1547 pounds per feet squared plus gamma times the head loss, or 10.7 psi plus the head loss. Okay. So now we've got our major and our minor head loss. Let's go ahead and calculate the minor head loss. So for our 90-degree threaded elbows, KL is equal to 1.5, and we've got 4 of those. For our wide open globe valve, we've got KL equals 10. Wow, it's a massive loss. And then from the figure, we know that KL is equal to 2 for the faucet. All right. So the minor losses, we've got gamma HL minor equal to gamma times the sum of the KLs times V squared over 2G. So here we've got equal to the sum of rho times the KLs times V squared over 2 is equal to 1.94 slugs per cubic feet times 8.70 squared over 2 times 10 plus 4 90-degree turns times that loss coefficient of 1.5 plus our faucet loss coefficient of 2. So we get 1321 pounds per feet squared, which is 9.17 psi. All right. Now calculating the major losses for this problem. So here we have HL major is equal to F times L over D times V1 squared over 2G. So from table 8.1, so for the drawn tubing, our epsilon is equal to 0.12345 zeros, and then a 5 feet. So that gives us a relative roughness, epsilon over the diameter of our pipe, of 8 times 10 to the minus 5 with no units, right? Because we're dividing feet by feet. All right. Now using that plus our Reynolds number that we calculated at the beginning of 45,000, we'll consult the Moody diagram, the Moody chart. And we can pick off that our friction factor is approximately 0.0215. Okay, if we were to use the formula, we would find the same answer. Okay, the total length of pipe L is equal to 15 plus 5 plus 10 plus 10 plus 20 feet is equal to 60 feet. So gamma times our major head loss is equal to rho F L over D V1 squared over 2 is equal to 1.94 slugs per cubic feet times 0.0215, that's our friction factor, times 60 feet over 0.0625 feet times 8.7 feet per second squared. We get that it's equal to 1515 pounds per feet squared, or 10.6 psi. Okay, finally putting everything together to solve for P1, the pressure in this basement at the entrance to this complex pipe system. And we get our final answer that the pressure in the basement at the beginning of the pipe system is 30.5 psi, right? So what do we use? We use the energy equation as the governing equation for this flow. We calculated separately our minor and major losses and added them up. And we also use the continuity equation, right, to be able to calculate the velocity given the flow rate Q. All right. So I'm going to talk a little bit about multi-pipe systems next, and then I think I'm going to do the second example, because this video is getting a little long, in a separate video. All right, so what about multi-pipe systems? We can either have 3 different pipes in series, say, or we can have 3 different pipes or any number of pipes in parallel. And the real question is, how do the head losses add up for these systems? So there's something really fascinating here. Let's look at the continuity equation. So for this particular system, we've got Q is equal to Q1 is equal to Q2 is equal to Q3, just by continuity, right? The flow rate has to be the same through all the sections of pipe. And then our head loss from A to B is going to be the head loss in pipe 1 plus the head loss in pipe 2 plus the head loss in pipe 3, right? So when you have pipes in series, the head losses just add up, right? So this is for this particular system with 3 segments of pipe in series. In the general case, for pipes in series, we've got our head loss is equal to the sum of HL major plus the sum of HL minor is equal to the sum of F times L over D times V squared over 2G plus sum of KL V squared over 2G, or in terms of flow rate, HL is equal to the sum of F over A squared L over D plus the sum of KL over A squared times Q squared over 2G, right? So that's for general, however many pipes you have in series. That's all pretty straightforward and intuitive, right? The flow rate is the same through all the pipes. The losses, head losses just add up. Now, when we come to the case of pipes in parallel, something really interesting happens, right? You can see the top pipe here, pipe 1, has got a diameter D1, and then we've got a different diameter D2 for the middle, and then a different diameter D3 for the bottom. So you would imagine that the losses are going to be different in these 3 pipes because we'll have different velocities, but that's not true. Due to the fact that a fluid particle could travel through any of these 3 pipes to get to the other reservoir, the losses through any 3 paths have to be the same. So we have this fascinating result that even though the pipes are different, the losses through each individual pipe in parallel are identical. Okay, so here we have, for this particular setup, we've got Q is equal to Q1 plus Q2 plus Q3. And then amazingly, in general, HL1 equals HL2 equals HL3. And then I'm just going to say dot dot equals HLN, right? So yeah, that's a nice result, and that's true anytime you've got pipes in parallel. All right, so I'm going to, for now, skip over this example 2 because we're at the end of our 50 minutes, and we'll just talk about looking forward. So problem solving session with Hyung-gun on Friday. I've asked him to solve these 4 problems. One of these, the first one here, is actually one of your homework problems. It's a tough problem, so I've asked him to just help set it up for you, right? He's not going to solve the whole problem, but he will help set it up. And then he'll solve these other 3 problems, which are similar, which deal with a lot of the same concepts as your homework. These problems are long, so I don't know if he's going to be able to get through all 4 of these. So, let him know, take a look at your homework early and let him know which ones you're most interested in. And then just a little note, the homework is a little bit longer. It's 6 questions instead of 5. Sometimes there's 5, sometimes 6. And also these questions tend to be a little long, right? It takes a while. They're sort of conceptually straightforward, but they can take a while to calculate through. So just plan ahead, take a look, make sure you don't need to go to office hours tomorrow or Friday morning. If you do, go ahead and hop on office hours or on Hyung-gun's lecture on Friday. All right, so hopefully I will have my annotator issues sorted out by Monday, and thank you everybody. I'll see you soon.